Okay, this is another video for special right triangles. And the one you just saw, that was a 45, 45, 90 triangles, but now we're going to talk about 30, 60, 90 triangles. So we're going to kind of do the same thing that we had done. We just got some different triangles. So we're going to find the missing length using the Pythagorean theorem. So in this one, um, we got something different. We're finding one of the legs. Okay, so this is our C value. This is our, we'll call this our B value, and this our A value. It doesn't really matter which one we call A or B, but based off the Pythagorean theorem, I know that the side length A squared plus the side length B squared is going to give us the side length C squared. So what I can do is, let's plug these in. We get x squared plus 3 squared is equal to 6 squared. And we're going to solve for x. Okay, so we end up getting x squared plus 9 is equal to 36. Let me subtract my 9 from both sides, and we end up getting that x squared is equal to, what is that, 27? So now what we can do is we can solve for x, and we take the square root of x squared and the square root of 27. And we end up getting this. We end up getting x is equal to the square root of 27. Now, this we can simplify, and we can split this up into the product of two square roots and say x is equal to the square root of 9 times the square root of 3. Okay, now I can take the square root of 9, and the square root of 9 is going to give me 3. So I get x is equal to 3 times the square root of 3. Okay, and I'm going to write that up over here. Okay, that x is equal to 3 times the square root of 3. Okay, now let's do this on another one. Okay, and let's do it for this triangle. This one's very similar. I'm going to call this C. I'm going to call this A. And I'll call this B, and we'll call this A. So I'm going to set up the Pythagorean theorem, and I'm going to get x squared plus 2 squared is equal to 4 squared. So I end up getting x squared plus 4 is equal to 16. Now I'm going to subtract 4 from both sides, and I'm going to get x squared equals 12. Now, if I take the square root of both sides, and I'm going to get x is equal to the square root of 12, that's an exact answer, but I can simplify this, and I can split this up into the product of two numbers, that being the square root of 4 times the square root of 3. And so I get x is equal to the square root of 4 times the square root of 3. Now I can take the square root of 4, and I get x is equal to 2 times the square root of 3. Huh. Well, that's interesting, because we got kind of a similar answer on the last one. So this is 2 times the square root of 3. Okay. So now let's try this one more time. Let's see if we see another pattern here. Now, based off of our pattern, I had seen this length was this leg of the right triangle was 3, and so this other length was 3 square root of 3. I also noticed that 3 is half the size of the hypotenuse, so the hypotenuse is double this length. Okay, same thing here. This leg was 2. The hypotenuse was double that length, and so this side was 2 times the square root of 3. So I see that same thing here. I see that this side length is 5, that my hypotenuse is 10, so my hypotenuse is double the length of this side. So I'm going to go ahead and make the bet that x is going to equal 5 times the square root of 3. Let's just see if we get that, okay? So then let's do that. Let's take x squared plus 5 squared is equal to 10 squared. So we end up getting this. We end up getting x squared plus 25 is equal to 100. Okay, now if I subtract 25 from both sides and solve for x, we get x squared equals 75. Now I want to solve for x, so it's squared. I'm going to take the square root of both sides to get rid of it. I get x is equal to the square root of 75. Now this is an exact answer. Okay, but I can split this up. I can simplify this, and I can say that, well, isn't this really just the square root of 25 times the square root of 3? Okay, is equal to x. Oh, man. I see it. So now I get x is equal to 5 times the square root of 3. Well, but look, It follows the pattern. Isn't that fun? That's pretty slick right there. I'll tell you what. So we find this out, okay? If one of my legs is half the size of the hypotenuse, then the other leg is going to be that smaller leg times the square root of 3. Huh. And so then I get the same thing here. 2 is half of 4, so this is going to be 2 times the square root of 3. 5 is half of 10, so this is going to be 5 times the square root of 3. Okay, so now we can kind of come up with this rule here. All right, and we call this a 30, 60, 90 triangle. Now, what you'll notice is that in a right triangle, if this length is, we'll just call it S for right now. That's what most books use. If this is length S and this is length 2S, then this length is S times the square root of 3. Okay, and so we're going to call this angle here 60 degrees, and we're going to call this 30 degrees. Okay, and this is going to work for every single 30, 60, 90 triangle. Okay, and what you'll notice about these is all of these triangles are proportional, which is why they have this relationship. Okay, and it was the same thing with the 45, 45, 90 triangle. So this is how we get the 30, 60, 90 triangle. It kind of just follows this pattern. But again, we have one leg that just has a length of S. The hypotenuse is doubled that. That's why it's being multiplied by 2. And then the third side is going to be that length S times the square root of 3. Okay, and this is very powerful. Again, you'll use this on the ACT exam. You will see this in trigonometry and in calculus, and you will use it a lot. So that's all I've got.